Hi everyone, in this video we cover the change of numeraire technique. We will spend a little bit of time discussing the basics of the approach, and we will then dedicate the rest of the video to the use cases, by which I mean we will cover the main examples where this technique is used. Right, so let's say you have some assets, say share of a stock, whose current price is S_T. So this T and the subscript is there because the price changes over time. It is a random quantity. And you can think of this price as in some units of cash, say 20 quid and pound sterling or US dollars. Now in our daily lives, we normally represent the prices in units of cash because the prices of many things don't change every minute. But when you're dealing in finance, the value of cash changes over time in relation to both other currencies, plus also in relation to its own value. 20 quid today is not equal to 20 quid tomorrow. So a common way to approach the modeling is to represent the price in terms of the value of the bank account. So you start with some initial value, say equal to 1, and then you keep reinvesting it at the risk-free rate. So over time it grows. In here we are assuming continuous compounding, and this why you have the exponential of the interest rate multiplied by the time. And if you have the value of the bank account at small t and you want to determine its value at capital T, then you will just compound the interest over the maturity, which is the time from small t to capital T. Here we are assuming the interest rate is constant, but if it's not constant, then we will have the integral of the interest rate and the exponent. And now you can scale the value of the asset by the value of the bank account, and this ratio is a main interest. Now this is just one asset out of many. So if you have an asset from say S1 to Sn, then you can also scale their values by the value of the bank account. And now if you have an option whose value we represent by V, then we can scale it by the value of the bank account as well. And then we know from the risk neutral valuation that this ratio is a martingale under the risk neutral measure. So normally you will see this risk neutral measure represented by Q, but here we represent it by B because we will be dealing with multiple numeraire assets. Now this risk neutral valuation requires some assumptions which we have covered in another video, so I'm not going to cover the details here, but those assumptions are usually satisfied. Now if you were to scale the value by another asset, say N, this numeraire asset has to satisfy certain properties. For example, it needs to be positive, and also if it pays dividends, then you will have to find a way to reinvest the dividends. But we are not going to worry about those details here. And similar to the risk neutral valuation, the ratio of the option scaled by the value of the numeraire asset will be a martingale, but under a different probability measure. So this is the probability measure associated with using N as the numeraire asset. It's similar to the risk neutral valuation, but in place of the bank account, we have another asset. Now we can take the current value of the numeraire asset to the right hand side. And now these two equations represent the value of the same assets, so they must be equal to each other. But we are going to use a slightly different trick, which is the abstract base formula. We have covered it in detail in another video, so again I'm not going to repeat the details, but it's very similar to the probability of A given B, but it's in more general term. And we now apply it to the first equation. So we write the B as it is, and then we express the expectation with respect to B in terms of the ratio of expectation with respect to N. So it's the same abstract formula, except in place of X, we have V divided by B. And now since the two equations represent the value of the same thing, so we can set the two equal to each other. Now you can simplify this expression, but it's a lot easier if we change the valuation time to 0, because then the term in the denominator on the right hand side is equal to 1, And then the two expectations are with respect to the same probability measure. So if the two expected values are equal, then you can deduce that the expression themselves will be equal to each other as well. Now we can cancel the common term and we can rearrange slightly, so we shift the n naught to the denominator and the b's on the right hand side to the left hand side, and we have the relationship between the Radon-Nikodym derivative and the ratio of the ratios of the asset prices. It is truly a magical relationship because it links the ratios of probabilities to the ratio of the ratios of asset prices. So it will come in quite handy when we want to determine how the expectation needs to change to reflect a new numeraire or vice versa. Right, so we can move to the use cases now. For the first example, we consider the zero coupon of maturity capital T as a numeraire asset. This one comes in quite handy in two cases, and one of them is when the interest rate is stochastic. So let's say you have a European call option on a zero coupon of maturity capital S, and the option expiry is at capital T. Capital S is supposed to be greater than capital T. This is the payoff at maturity, but we are interested in its current value. So we use our risk-neutral valuation formula and we can substitute for the payoff. And now, as you would have expected, this one simplifies when we use the zero coupon of maturity capital T as the numeraire. So we need to change the expectation from B to capital T, which is the expectation with respect to the probability measure associated with using the zero coupon of maturity capital T as numeraire. And we know the two expectations are linked as follows. We have covered this one in another video, but if you forget, then you can write the expectation with the integral and you can see the dQt and dQt on the right hand side cancel, so the two are indeed equal. And we can now replace our expectation. So we just multiplied the payoff by the Radon-Nikodym derivative and changed the expectation with respect to B to expectation with respect to capital T. Now we need to write this Radon-Nikodym in terms of the asset prices. We have the identity. We just need to replace the asset N by the zero coupon of maturity capital T. And in the numerator, we have also moved the T from the subscript to the arguments to align it with what we have in the denominator. And we can now substitute for the Radon-Nikodym and then try to look for cancellations. So these B's cancel and the value of the bank account at small t is known at the valuation time. So we can take it out of the expectation and use it to cancel the same term on the left hand side. And then the price of the zero coupon of maturity capital T at capital T is equal to 1. And then the price of the zero coupon at small t is known at small t. So we can take it out of the expectation. And here we go. And as expected, the expectation has simplified because the discount factor has gone out of the expectation. For our second example, we continue with the interest rate. And now we consider the simple forward rate. So let's say we divide the interval from t0 to t_n into sub-intervals. And let's consider the simple forward rate from ti-1 to ti. And we will be using the zero coupon of maturity t_i as the numeraire. Now we write the simple forward rate in terms of the zero coupon prices. We have covered this one in the interest rate series, so we're not going to repeat the derivation. But essentially what we have on the right hand side is the relative change in price when we change the maturity from ti to ti-1, and then we have divided it by the duration of the interval. So it's just like the growth rate per unit time, and that's what the simple forward rate is, right? Now if we move the price in the denominator to the left hand side, then what we are left with on the right hand side is the linear combination of two assets. So we can say that F times P is the price of a traded asset, and we can treat this combination as a traded asset. And before proceeding, let's express the Radon-Nikodym derivative that we're going to be needing when changing the measure from B to T in terms of the prices of the assets. So we have just replaced N by the zero coupon prices, and we can simplify the ratio on the right hand side slightly by moving the terms in the denominator upstairs. Now let's represent the value of this F times P by V, and we use the risk neutral valuation. Again, we will have to change the expectation from B to T. So we multiply it by the Radon-Nikodym derivative and change the expectation from B to T. And then we substitute for the Radon-Nikodym and then look for the cancellation. So the B's cancel and these B's cancel as well, because the value of B at time small t is known at small t, and the price of the zero coupon at small t is known, so we can take it out of the expectation. Now this is the value of F times P, so we set it equal to F times P, and then we cancel the P's, and what we get is truly magical, that the simple forward rate over an interval ending in TI is a martingale under the probability measure associated with using the zero coupon of this maturity as the numeraire. For the third example, we continue with the interest rate, and now we consider the instantaneous forward rate. So it is like the simple forward rate, except that the length of the interval goes to 0. So we will have the zero coupon bond of maturity capital T, and we recall our risk neutral valuation. We can shift the B to the right hand side, and because it is known, so we can take it inside the expectation. And then let's recall the relationship between the values of the bank account at two different times under random interest rate. Here we have the small b divided by the capital B, so we take the exponential to the other side, which means the sign of the exponent becomes negative, and we can substitute it for the ratio of the values of the bank account. And now we take the derivative of this with respect to the maturity. And then on the right hand side, assuming that we can exchange the derivative and the expectation, we just apply the derivative of integral rule. Now we need to link this to the instantaneous forward rate as you expect. So let's recall that the price of a zero coupon can also be written in terms of the current values of the instantaneous forward rates. So these are the forward rates at small t for different maturities between small t and capital T. We take the logarithm of both sides so that we get rid of the exponential on the right hand side, and then we take the derivatives of both sides with respect to capital T. On the right hand side, we just apply the rule for the derivative of integral. And then on the left hand side, we know that the derivative of the log of p is equal to 1 divided by p times derivative of p, and the right hand side stays as it is. And we then shift p to the right hand side, and now we can substitute this for the derivative of p with respect to capital T. We now isolate the instantaneous forward rate on the left hand side, and we then recall that the price of a zero coupon can also be written in terms of the short rates. So R underscore S here is the short rate. So it is like the future observed values of the instantaneous forward rates, and because these will be observed in the future, so we need to take the expectation, and we can substitute this for P. And now this looks very much like the right hand side of the abstract base formula, and to see it more clearly, let's recall that the Radon-Nikodym of the measure capital T with respect to the measure B can be written as follows. So this is just the ratio of the ratios of the asset prices, right? And we know the zero coupon pays 1 at maturity, and we can simplify the ratio by moving the terms in the denominator upstairs. And we then recall the relationship between the values of the bank account at 2 times. and substitute it here. So it is similar to what we have inside the expectation, but we have this extra 1 divided by p. But this p doesn't count because we have the same term in the numerator and the denominator, so they will cancel each other. So the exponential term we see is nothing but the rate-on negative derivative of the measure t with respect to the risk neutral measure. And then this is nothing but the right hand side of the abstract base formula. So we know it equals the expectation of r with respect to the measure associated with using the zero coupon of maturity capital T as the numeraire. And what we see is that the instantaneous forward rate is the expected value of the future values of the short rate under the measure associated with using the zero coupon of maturity capital T as the numeraire. Right, so that's enough of the interest rate. There's another interesting case of the annuity measure which is used in the swaps valuation, which I will leave you guys to research for yourself. And we move to the exchange options now. So let's say you have an option which allows you to buy an asset A for an asset B. And this is the payoff at maturity. And we are of course interested in its current values. So we use the risk neutral valuation and substitute for the payoff. And as you expect, this one will simplify if we use one of the underlying asset as the numeraire. So we will choose the asset B. So we want to change the measure from risk neutral to the measure associated with using the second asset as the numeraire. So we just multiply the payoff by the rate-on negative derivative and change the expectation from B to S underscore B. And we then know how the rate-on negative derivative can be expressed in terms of the ratio of the asset prices. So here the asset in the denominator is the second asset, which is S underscore B. And we can simplify the ratio and then substitute this for the rate-on negative. And then look for cancellation. So these B's cancel and these B's cancel as well. Now we have the ratio of the prices of the second asset. So the one is known as small t. So we take it out of the expectation, and the other one will become known at maturity. So we take it inside the maximum. And we have a very simplified expectation. So it's very similar to the Black-Scholes, except that you will have to specify the dynamics of the ratios of the two assets. And for the final case, we consider an option that involves the foreign exchange. So let's say you have a contract that allows you to buy a foreign stock for domestic price. So let's say you have a stock price in pound sterling and you can buy it for a fixed USD price at maturity. Now, if we want to determine its payoff, then we have to convert the two to the same currency. So let's say we multiply the strike price by the exchange rate to convert it into the foreign currency, and this will be the payoff of the option in the foreign currency. And we recall the risk neutral valuation using the bank account and the foreign currency as the numeraire, and we can substitute for the payoff. And now, as you would have expected based on the settings, that this one will simplify if we were to use the risk neutral measure associated with the domestic bank account. So we change the expectation. So we multiply by the rate-on negative derivative and change the expectation from B underscore F to B underscore D. And we then need to express the rate-on negative derivative in terms of the ratio of the ratios of the asset prices. The only complication here is we have to multiply one of the price by the exchange rates, so they are in the same currency. Otherwise, the same relationship we saw before. And we can simplify it by moving the terms in the denominator upstairs. And then we can substitute it for the rate-on negative inside the expectation. And then look for cancellations. So these B's cancel. And these B's cancel as well, because the value of this bank account is known as small t. So we can use it to cancel the same term on the left hand side. and the values that are known at small t, we can take them out of the expectation, and then what will become known at maturity, we take them inside the maximum. And if we shift the exchange rate to the left hand side, then we will have the option value in terms of the domestic currency. So you can see the expectation has simplified, or at least has changed. Right, so these are the main use cases we wanted to cover. Of course, there are many other use cases, but hopefully we have covered enough variety so that you can understand this technique when it's applied in practice. Please give a thumbs up if you would like to see similar videos, and I look forward to seeing you in the next video.